I had it interfering on the audio with the speakers. Okay. Oh, hi. Would you please take a look at an electromagnetic spectrum? There's one in your textbook, and a beautiful, beautiful, beautiful color one it is, because it's got the visible spectrum, the colors of the rainbow, all kinds of little remarks on here. The EM, or electromagnetic spectrum, is representing all of light. Over on the right side, I'm going to go ahead and mark it up as low energy. And our low energy stuff now is going to be considered TV, radio, and basic communications. So we have things like cordless phones, cell phones, walkie-talkies that adults might have and keep an eye on their kids at Disneyland and stuff, the little tiny pocket ones. Just to the left of this, we get a little bit higher in energy, and this is what's known as the microwave region. All of these things are forms of electromagnetic radiation or light. They'll all travel at the same speed. The microwaves do that very unique thing of rotating water molecules. So we take advantage of this for cooking our foods. Just over to the left, we have infrared, or what we call IR. You and I don't see IR. Television remote controls often operate off of IR. There's a neat little demo you can do. You can point the TV remote control at your eyes and you won't see anything. And that's because our perception happens to be over a little bit further and we don't see in the infrared region. However, many cell phones with the cameras detect IR, and they'll go ahead and visually represent this on the screen. So you can aim your cell phone camera at a TV remote control, start pressing buttons, and you won't see the flash on the remote control, but you'll see it on the screen of your camera while it's on. It's kind of neat. The visible spectrum is next to the IR, and the visible spectrum is made out of the colors of the rainbow. And we have a little memory technique. We call it ROY, and I'm doing it backwards because I started on the right with low energy. ROY stands for red, orange, yellow, colors of the rainbow. G, and then BIV. Many students remember this from middle school or so. The colors of the rainbow: red, orange, yellow, green, blue, and violet. I wrote indigo with a lowercase I because really that's one flavor, and we call it violet. Next to visible is ultraviolet, and these things over on the left are higher in energy. So these are used as communication devices and sensing in outer space. Others down here on the Earth's surface use them to tan themselves, higher energy than visible light. Next is X-ray, and X-rays are dangerous. They're deleterious to human tissue. Bad stuff. X-rays are very high in energy, and I left a little bit of space out at the end for gamma radiation. So the small Greek symbol gamma radiation. Gamma comes from our sun, distant stars, and nuclear reactions. It's very, very high in energy. The stuff over on the right is low in energy. We also call it long wavelength. Long wavelength. We have a nice symbol that's fun to draw for wavelength. It's the Greek symbol lambda. It's like an upside down, twisted something, lowercase y. Wavelength. And what's meant by wavelength is, that's a long wavelength. I'm doing a repeat unit where the wave goes up and down and up, and then it's all ready to start again. So that's one wavelength. Over on the left side, these things that are high energy, like gamma and X-ray and ultraviolet, they have short wavelengths. And I'm going to put many of these because I've got the room up on the board to do many of these short wavelengths. A wavelength is a repeat unit. You can pick any point you want and say it's going to repeat. And so that distance there is the wavelength. I can label that lambda, the wavelength. And you don't have to start at the top. You can start in the middle, the bottom, halfway up, as long as you do a repeat unit. There's another feature to waves that we like to speak of, and that is frequency. Frequency. Things that have short wavelength are high frequency. Things that have long wavelengths are low frequency. Frequency can be described as events per unit time. We like using events per second. What's meant by that is all of this stuff is traveling very fast, the speed of light. If you have a long wavelength and it travels in front of you, you're going to have some of these pass by your face every second. If you have a short wavelength like this, many more are going to pass by you in 1 second. Because if I keep a constant rate, I'm going to have this wave going this fast. There's one. But if I have this one and I move at the same rate, I probably had about 4 or 5 go by me. So we have frequency as being events per second, or how many waves pass by your face in 1 second. Up on the board I've written a couple of equations. This one says that this letter, which is the small Greek symbol nu, N-U, which is the frequency, is inversely proportional to the wavelength. So if the wavelength is long, like over here, the frequency is small, and that's low frequency. The C there, many of you might know this, is the speed of light. 3.00 times 10 to the 8th meters per second without interference, or what we call in a vacuum. Let's go ahead and take a look at a particular light and calculate things like its frequency, and then we'll follow up by calculating its energy, because that's going to help us determine the behavior of electrons. The light that's coming out of the sun is said to be white light, and that's a blend of all the colors. And when that light hits an object and we perceive, say green in this case, what's happening is the green has an energy associated with it. Hits our eye, we process that information and say green light. We can calculate that. For example, consider a green light that has a wavelength of 530 nanometers. And you can check this in your electromagnetic spectrum, and you'll find that 530 is probably just to the right of the solid green region. Something a little pale like this wood ball has been painted. So we've got green light with a wavelength of 530 nanometers. Let's go ahead and calculate its frequency. So frequency is equal to the speed of light over the wavelength. The speed of light is going to be taken to be 3 times 10 to the 8th. Oops. Yeah. Meters per second divided by 530. Now, I can't leave this in nanometers because I've got meters up here, and I'd like to convert the 530 to meters. There's a very, very quick way to do it. Slap a times 10 to the negative 9th on there and call it meters, because a nanometer is 1 times 10 to the negative 9th meters. So now our meters cancel, and note that our units are not seconds. Our units of frequency are going to be events per second, or 1 over seconds, because seconds is in the denominator. So in a moment, we'll calculate the frequency, and the units will be 1 over seconds. I continue to use the units 1 over seconds. Many of these people out there know these units as being a Hz, a hertz. But I like the seconds because seconds cancel and we show all our work. So I'll take 3 times 10 to the 8th meters per second divided by 530 times 10 to the negative 9th meters, and come up with 5.66 times 10 to the 14th events per second. What we're speaking of is this many wavelengths, just an astronomical number of wavelengths are zipping by your eye in 1 second. And that's because light travels so quickly and this wavelength is so small. Let's calculate the energy of this. We have an expression courtesy of Max Planck. Max Planck went ahead and said the energy is equal to a constant, which is named Planck's constant, times the frequency. This constant is 6.626 times 10 to the negative 34th. Now for units, this is going to have an energy component to it. The units of Planck's constant are joules times seconds. And really, this is for 1 photon, 1 packet of energy. So I'm going to sneak in this little photon underneath here. So that is H, Planck's constant, the energy times seconds per 1 photon, times our frequency that we just calculated, 5.66 times 10 to the 14th, 1 over seconds. So frequency, please think of things like high and low frequency. If something has a high frequency, that's a lot of events per second, like a little yapper dog. Lots of barks per second. And if something has a low frequency, might be a bigger dog going woof, Lower frequency would be fewer events per second. And we're thinking in terms of light, so we're thinking about how many of these waves pass by our eye per second. So the energy of this, I come up with energy being equal to 3.75 times 10 to the negative 19th off of my calculator. The seconds cancel, and we end up with joules of energy for one little photon, one packet of energy. If we're interested in calculating how much energy it is for 1 mole of photons, multiply this number by Avogadro's number, 6.022 times 10 to the 23rd. I'll make a little note off to the side. For 1 mole, we would take that number and multiply it by Avogadro's number, 3.75 times 10 to the negative 19th joules per photon times 6.022 times 10 to the 23rd. The units of Avogadro's number, photons per mole. This many photons in 1 mole. And I come up with, let's see, 225,859, that's what my calculator tells me, joules per mole. Far too many sig figs, and quite an uncomfortable number, 225,859. If I divide this by 1,000, I'm in kilojoules per mole, so I'm going to call it 226 kilojoules per mole. We just did an energy calculation.